Okay, now I've hopefully enhanced this picture a little bit. Implicitly, the origin is here, so this picture would go right here. Now I've drawn a VR and a VL and a VC. The problem you were given was to sketch the phasor diagram for a circuit with a given capacitive reactance, a given inductive reactance, and a given resistance. Okay, so a couple of things that we saw last time, that the integral of I of t, which is the charge on your capacitor, which is then going to be proportional to capacitor voltage, is 90 degrees behind I of t, assuming, of course, that your current is a sine or a cosine function, a sine of omega t plus some initial phase angle, which we might call phi naught, or cosine thereof. Okay? So if I of t is a sine or cosine function of that nature, some amplitude, times a sine or cosine of omega t plus phi naught, let's say. Doesn't matter what phi naught is, when you take the derivative, you're going to find that, when you integrate I of t, you're going to find that the antiderivative is 90 degrees behind I of t. And that the derivative of I of t is 90 degrees ahead of that, so that I of t is 90 degrees behind the derivative. Now, the capacitive reactance and inductive reactance are defined analogous to the resistance, in that you multiply any of these by the current and you get the magnitude of the voltage across that current, across that circuit element. So you multiply resistance times current. We're very familiar with that. That's Ohm's law. It gives you the voltage across the resistor. Well, if you multiply capacitive reactance, X sub C, by the current, you get the voltage across the capacitor. If you multiply the inductive reactance, X sub L, times the current, you get the voltage drop across the inductor. And the capacitive reactance and inductive reactance come right out of this process of taking derivatives and or out of the differential equations. And we find that the capacitive reactance, the thing you would multiply by your current, is 1 over omega c. Now the 1 over omega comes because the charge on the capacitor is an integral of your current. When you integrate sine or cosine of omega t, you're going to get a 1 over omega, reverse changeable. And that's where the 1 over omega comes. The c's in the denominator because the voltage across the capacitor is 1 over c times the charge. Now, when you do the inductor, you're going to take the derivative of the current because that's the rate at which the current's changing. Current changes, changing the magnetic field, causing an induced voltage opposite to the one you're trying to drive the current with. And when you do that, out of the chain rule, you're going to get an omega. That's sine or cosine of omega t. When you take the derivative, you're going to get an omega times the other function, and maybe with a minus sign, depending on which function you use. And the phi naught, if it happens to be in there, doesn't make a bit of difference when you take the derivative or integrate. It just goes along. Okay. So that's where these expressions come from. It's not that difficult to understand. But right now, let's focus on the fact that VL is 90 degrees ahead of the current. The voltage across the resistor is in the same phase as the current. The voltage across the capacitor is 90 degrees behind the current. So when you draw these vectors, you draw the current, the voltage across the resistor in the same direction as your current would be. Whatever omega t plus phi naught happens to be, that tells you in what direction you draw this thing. Then you draw your VL 90 degrees ahead of that, and you draw your VC 90 degrees behind that. Now these magnitudes depend on R and X sub C and X sub L. Your resistance and your two reactances. Okay, the capacitive and inductive reactance. They just determine the magnitude. You multiply any of these by the current so that if your resistance and capacitance and inductance are in some ratio, then these vectors will have lengths in that same ratio. So if you find that your capacitance is much smaller, well, you draw this vector smaller. If you got a bigger resistor, you draw this vector bigger. Now, of course, the reactance changes with omega. If omega gets higher, the capacitive reactance decreases. Of course, that's as we saw before, because a quickly changing current isn't ever going to have time to build up much charge on a capacitor. So there's not going to be much voltage in the capacitor, so it's not going to interfere much with what's going on in the circuit. And similar reasoning for the inductor. If omega is high, then you're going to get a big back voltage, and you're going to have a lot of resistance, of effective resistance to the buildup of current because of that. Okay, well, you want to understand those little things, and you want to be able to put them together so you completely understand this picture and why it works. But the bottom line is, for the problems that were posed on this document, I just gave you a number for VR, well, so many ohms, this is so many ohms, this is so many ohms. So when you draw it, you can draw your resistance, your VR vector in any direction. And then once you've chosen that direction, you put your VL 90 degrees ahead, your VC 90 degrees behind, and you put the sizes of these vectors, the lengths of these vectors, in the proportion to their given R, XC, and X sub L. That's all there is to it. And then you imagine what happens if this thing rotates around the unit circle. And that's what we've done over here, and that's what we're going to talk about.